So we'll come back to that topic in a minute, but first we're going to talk about different types of solutions. So a solution has two components, the solvent and the solute. There's only one solvent, but there can be many solutes. And the phase of those solvents and solutes can be anything. So you can have gas solutions where the solute is a gas and the solvent is a gas. An example is the air we're breathing right now. So there's a lot of nitrogen, that would be considered the solvent. And then there's oxygen, that would be the solute. And then there's also argon and carbon dioxide and other things. So it's all a gas. You can also have a liquid solvent with either a gas, a liquid, or a solid solute. So seawater would be salt and water. You take some salt, which is a solid, and you mix it into water, it dissolves, and the solution is a liquid. You can have liquids mixed together. Vodka is a solution of ethanol and water. So ethanol is a liquid and water is a liquid, and the mixed together, it's a solution. You can also have gases dissolved in liquids. Club soda has carbon dioxide, which is a gas, dissolved in water. Okay? You can also have solid solutions. The most common of these are metal alloys. An alloy is a solid mixture of different metals. So brass is copper and zinc. They're mixed together thoroughly. It's homogeneous, but they're not chemically bonded to each other. It's not a compound. And the composition can vary. So solid dissolved in a solid. You can also have gases dissolved in solids and even liquids dissolved in solids. And so any combination is possible. The solutions we use most often are aqueous solutions. And we've used this word aqueous before. That means that water is the solvent. Whatever that is dissolved in water. Any questions? So any given solvent, such as water, is not going to dissolve all possible solutes. Can you think of something that does not dissolve in water? Oil. So you get oil on your hands when you're, maybe greasing a pan, you got Crisco on your hands. It will not dissolve in water. It just doesn't. Whether it dissolves or not, whether it is soluble or not, depends on several factors. One of those is the types of intermolecular forces. And so we've talked about that. Oil is nonpolar, water is polar. Their intermolecular forces are very different, and so they don't mix well together. They don't make a solution. We've also talked about the solubility rules for ionic solids. You think about an ionic solid, it's like, well, it's got ionic bonds, it's got ions in it, and water's polar, and so we should have these ion dipole forces, and they should dissolve. Many ionic compounds do dissolve in water, but not all of them do. And so whether they dissolve or not is a bit more complicated than just the types of intermolecular forces. So when we talk about solubility, we talk about the amount of substance that will dissolve in a given amount of solvent. So how much sodium chloride can dissolve in 100 milliliters of water? Well, there's a number. We can find it out by doing an experiment. This is a picture of club soda. So we've got carbon dioxide molecules dissolved in the water. And the reason that it fizzes here is because we've released the pressure, and so the gas is coming out of solution, and that's what gives it the fizz. Same thing happens with soda. So another thing about the solubility is it depends on this tendency towards mixing. Many physical systems tend towards a lower potential energy. I've talked about pianos falling out of second floor windows. The potential energy is high when something's elevated above the ground. You release it and it tends to go to a lower potential energy. This happens in all sorts of different situations. But not everything can be explained through just lowering of potential energy. So if we think about a container that has two gases, neon and argon. They're both noble gases. They're not going to interact with each other. If we remove this barrier, what's going to happen? They're going to mix. If we think about what do gas molecules or gas atoms here do, we talked about the kinetic molecular theory of gases. Gases are composed of tiny particles, and they're going to move in a straight line until they hit something. They're going to bounce off in an elastic collision and just keep going. And so these guys are just zinging around in this container. When we remove the divider, then they'll mix because they're not going to run into this barrier anymore. This mixing of two ideal gases does not lower their potential energy in any way. So lowering the potential energy does not explain why things mix. We need to introduce another concept called entropy. Entropy is a measure of energy randomization or energy dispersal in a system. What happens when those two ideal gases mix is that the kinetic energy of each gas becomes spread out or dispersed over a larger volume. We think here about neon. Okay, each neon atom has kinetic energy, right? And when the divider is here and these two gases are separated, the kinetic energy of the neon is contained to half of this big box. We remove the divider, and now it spreads out, and now the neon kinetic energy is spread out over the entire thing. That's an increase in entropy, an increase in the dispersal of energy. So substances will mix because of this pervasive tendency for energy to spread out whenever it is not restrained from doing so. Entropy also explains why thermal energy moves from hot objects to cold objects. A hot object has more kinetic energy, more thermal energy than a cold object. If those two objects are in contact with each other, the energy will spread out until they're both at the same temperature. It's a dispersal of energy. Entropy is kind of a hard concept to thoroughly understand, and I don't expect you to have a thorough understanding of it, but a general understanding. So dispersal of energy. You can also think of it in terms of a measure of disorder. So if you think about a deck of playing cards, and it's a brand new deck, and they're all lined up, by suit and in order and everything, and they're all, nice together. If you drop that on the floor, what happens? They spread out, right? Do they stay in order? Do they fall into a nice grid pattern? No. Think about leaves on a tree. Leaves on a tree branch are actually ordered. You go up the branch and there's leaves at usually regular intervals and they're all attached at one end. And then fall comes and the leaves fall, and what do? They go all over the place. And the wind comes and they blow all over the place. And this is what happens at my house. My house is a demonstration of the increase of entropy. You wash the dishes, you put them away. You wash the clothes, you put them away. You come home from work, there's stuff everywhere. Dispersal of energy, increase in randomization. Okay? That's natural, and it happens spontaneously. You do not see things just coming together into an organized pile. It doesn't happen. That requires the input of energy to fight against entropy, to lower the entropy. That's where Mom comes in and picks up all the Lego blocks, right? Any questions about entropy? I love and I hate entropy at the same time. Intermolecular forces do play a part in whether something forms a solution or not. So we've talked about this a little bit. We've got dispersion forces between things like heptane and pentane. These are hydrocarbons. They've got nonpolar bonds, and the whole molecule's nonpolar. They just have the dispersion forces. Dipole-dipole forces occur between two polar molecules, and so two polar molecules will tend to form a solution. Hydrogen bonding, ET phone home, you have to have hydrogen bonded to fluorine, oxygen, or nitrogen in a polar molecule. So ethanol and water are both polar, and they both have hydrogen bonded to oxygen, so they will engage in hydrogen bonding. Hydrogen bonding is stronger than dipole-dipole forces. And then you have the ion dipole force, where you have an ion interacting with a polar molecule, such as water. And so you have a dipole interacting with an ion. If the forces are similar in strength, then a solution will probably form. Some of these slides are going to be not so aesthetically pleasing because I didn't have time to adjust them all. I just switched from the more square aspect ratio to the wide, and I think I missed some like this one. So intermolecular forces in a solution are going to exist between the solvent and the solute particles. They'll exist between the solvent particles with other solvent particles, and they exist between the solute particles. So that's a lot of sol words. So here we have the solvent and the solute. There's interactions between those, between the solvent molecules themselves, and between the solute molecules themselves. Okay? And this one, no, there it is. So if the interactions between the solvent and solute molecules are strong relative to the interactions between the solvents with themselves and the solutes with themselves, then a solution will form. If those interactions are approximately the same, a solution will form. If the solvent-solute interactions are weaker than what's present within the solvent and within the solute, the solution may or may not form. It depends on how much less it is. So here's one of my stupid analogies. So my husband is of Japanese descent, so we'll make him the blue one there. And I'm of Swedish descent. So if you speak about an ethnic group that you are a member of, then it can't be considered rude, right? You're talking about yourself, and my husband will not take offense. Okay, so let's say you have a bunch of Japanese people who only speak Japanese, and a bunch of Swedish people who only speak Swedish, and you throw them in a room together. What's going to happen? There's going to be clumps of Japanese people speaking Japanese to each other, clumps of Swedish people speaking Swedish to each other, right? They're not going to mix uniformly. That makes sense to us. The interactions between someone who only speaks Japanese and someone who only speaks Swedish are going to be really strained, right? It's hard to talk to someone who doesn't speak the same language. So that's really natural. The same thing will happen with a solvent and a solute if they can't communicate with each other. I think of the intermolecular force as being a method of communication. It is a force of attraction, and you are more likely to be attracted to someone that you can communicate with. So if, as is actually true, the Japanese and the Swedish people all also speak English, will they mix together? Yeah, they probably will mix together because they can communicate with each other. Does that make sense? So it's the interactions within the solvent, between the molecules of the solvent, versus the ones between the solute. If those interactions are very strong compared to the ones between the two groups, mixing isn't going to occur. But if they're roughly the same, then mixing will occur. Any questions? So we do gain entropy when things mix together, but if those solvent-solute interactions, this is like a tongue twister, this slide. If the solvent-solute interactions are very weak compared to the interactions between the solvent and between the solute, you're breaking strong interactions and forming weak interactions, and that doesn't make up the gain in entropy doesn't make up for the energy loss caused by breaking strong connections and making weak ones. So what should you be able to do with that? You should be able to predict whether each of these compounds is going to be soluble in hexane. Okay, so it doesn't give you the formula of hexane. I did teach you how to write the formula for hexane. Hexane, the A-N-E tells us that this is a hydrocarbon with all single bonds. And what does the prefix hex mean? 6. 6 carbons and then a bunch of hydrogens on it. Is that going to be polar or nonpolar? Nonpolar. A carbon-hydrogen bond is nonpolar. And so this is a nonpolar solvent. So when you're asked to predict whether things will dissolve or not, I expect you to do that based on types of intermolecular forces. So you look at water, and what's the strongest force that water has? Hydrogen bonding. So this has hydrogen bonding. This is polar, right? I don't know why I put a dot there. Hydrogen bonding. This is polar. Is polar water going to dissolve in nonpolar hexane? Nope. They speak different languages. They're not going to mix together very well. So that one's not. Ammonia. Is ammonia polar? You might remember, but you can't tell just by looking at the formula, because it kind of depends on what's going on with it. So ammonia is 3 hydrogens bonded to a nitrogen. Are there any lone pairs? Yeah, there's going to be a lone pair on the nitrogen. So you have to count up the number of valence electrons, make sure that you account for all of them, give people octets, etc. This is the Lewis structure for ammonia. Is it polar? Yeah. There's a lone pair on the central atom. It's a polar molecule. So ammonia is polar. Oops. Is it going to interact with hexane? No. There's propane. Polar or nonpolar? Nonpolar. All carbon-hydrogen bonds. Is that going to interact with hexane? Yeah, it probably will. How about hydrogen chloride? Polar. So here we've just got 2 atoms, hydrogen and chlorine. And the shortcut, instead of trying to compare electronegativity, is to decide